Thank you very much. I'm humbled to be here and to be able to have the opportunity to talk with you on your Saturday morning. This is really great to see so many of you here on the weekend. So it shows a lot of enthusiasm for physics. So like Kevin said in his gracious introduction, I think I am still the newest professor here in the physics department, which our department head constantly reminds us of. So I've been here.
That goes on in the department.
That's right. So all the department meetings, he always jokes about this. So I've been here for 2 years, and my laboratory is upstairs 2 floors, kind of diagonally that way, and you all are welcome to come visit. Just send me an email, and we can arrange for you to tour the lab. So I am part of the burgeoning atomic physics group here at Illinois. It's a group the department has been building up for the last 10 years. I'm the 3rd member of it, and we'll tell you about some of the new and exciting physics that can be done in modern atomic subdiscipline of physics. So with that, let's begin on some things that I've worked on and some things that are particular to my research program, although of course there's many other types of things that one does in the atomic physics field. You'll see a lot this word AMO, sometimes I'll say it. AMO is the acronym for the type of physics that we do. It's called atomic, molecular, and optical physics. It's a catch-all phrase for people who use atoms, molecules, and photons to study quantum physics. So what I do in particular is try to devise new ways to manipulate atoms so that we can create new devices and create new quantum regimes that we can study and explore. So one of those tools that I've developed over the last 10 years is called the atom chip. And this is an example of one that I made when I was a graduate student at Caltech. And it's an example of a way in which we can move atoms around above a surface and couple them to photons. So hopefully it'll be a little bit more clear how these things work in the course of this talk. Okay, so if we're going to try to do new and exciting things with atoms, how can we create technology with that if the atoms themselves are really, really small and they're really fast? So there may be some notion that you have that, gee, it'd be great to assemble nice devices and do honest-to-goodness nanotechnology or sub-nano, pico technology. But we have to start very, very slowly and just develop the tools to hold on to the atoms that are smaller than a nanometer. So your hair is, it's about 10,000 times smaller than your hair, or much smaller than that, 100,000 times. The other thing about atoms is that not only they're small, but because they're so small, they actually move very, very quickly in a room. So in the atmosphere, generally, atoms are moving around at several hundred miles per hour. Or you could also say several, like 100 or 200 meters per second. So even if you could find a tweezer, a magical tweezer that allows you to hold on to, that if they're still, you can hold on to them, well, just catching them in the first place is going to be really tough. It's kind of like the Karate Kid where you're trying to get that fly. You got the tweezer, but they're going around too fast. So how do we simultaneously slow the atoms down and then hold on to them? Well, that's something that we've discovered how to do in the last 15 years or so in the field of atomic physics. Now, before I tell you how we've done that, there's a question that I have to explain, and that is the fact that atoms are inherently quantum particles, generously, especially in TV programs. But the word quantum for us means that, well, it's not what we normally experience, okay? In our normal everyday lives, our intuition is more what we call classical or Newtonian. If we kick a soccer ball, we can predict with infinite accuracy, in principle, in the classical world, as long as it is classical, where that will go. Of course, everything is quantum mechanical, even if it's a soccer ball. It's just the quantum mechanical properties of the soccer ball tend to get washed out when it becomes so big. So when you get things that are really small, those quantum mechanical properties cease to wash out. And your intuition about how you would go about kicking a soccer ball or moving something go completely out the window. Okay? So it's kind of like if you're at a beach and you look very far away at the sand dunes. You see that they're nice rolling waves and, okay? So the same kind of hand-wavy analogy, our everyday classical world, the physics that governs that is very different than when you get very, very small in the atoms. And basically, when we're looking at atoms, molecules, photons, and even smaller things like quarks, neutrinos, generally our classical physics does not work anymore instead of mathematical tools, okay? So you may see, okay, well, how do I come to understand any of this math? Well, we don't need to go into math. We can just say some very basic things that are different. You've never heard of particle wave duality. So particle wave, objects are particles, and some people say waves. Well, they're both. It all really depends on how you observe the system. So sometimes when you observe electrons, for instance, the experiments advise they can take atoms on a surface of paper and position them around into a cloud. They form the cloud. The electrons inside this metal, you can see that on the surface they start to act as a little wave. So you can see waves of electrons in a little puddle being corralled by the atoms. Okay? Well, here you actually see the particle-wave duality directly. The atoms look kind of like particles, but the electrons look like waves. Okay? But I claim that there are other experiments where it's completely consistent to think of the electrons just as particles. Say in a particle accelerator, when you collide electrons, they're kind of like particles. Okay, so in quantum physics, we have to do some mental gymnastics to at once think of things as particles and also waves, depending on how we observe them. So that's one example. There's several other examples of quantum weirdness, but that's one important one. Okay, so why is quantum behavior important? Why am I telling you about this? Well, from a technological standpoint, these are things that we have to deal with. Okay? If we're going to make better, smaller, faster computers, eventually we're going to have to deal with quantum mechanics. So this is a graph of Moore's law. It's something that some of you may have heard about. Gordon Moore, I think in the 60s or 70s, came up with a prediction that in some sense, the power of a computer per fixed area will double every 2 years. Okay? So the number of transistors that you can fit on an integrated circuit, or the processing speed. And gosh, he was right. Okay? This is what has driven our economy in some sense, is the fact that Moore's law is held. Okay? It's not a law like a physical law, like the laws of quantum mechanics or Newtonian laws, but it's something that is a law from the standpoint of Silicon Valley entrepreneurs and so forth. So if you look at the processing speed as a function of time, so this is going down from 1999 to 2000, and as we go in time, you see that the number of transistors that can fit on an integrated circuit gets larger. Same time, the processing speed gets larger. Okay? But what you could also take from this is that if you have more transistors per unit area, at some point, those transistors are going to get so small that it's basically a single atom or a single electron that comprises that transistor. You can't keep dividing things down infinitely. Eventually, you're going to get to the atomic scale. Well, I just told you that when you get down to the atomic scale, all your intuition goes out the window. Soccer balls don't behave like soccer balls anymore. Transistors don't necessarily behave like transistors anymore. Your computer will not work like you want it to do. So what do? Well, the quantum realm is already here. We're already trying to deal with this. And a few years ago, some folks at MIT tried to make it a transistor out of with a single electron. So this is the gate, the drain, the source that's manipulating just a single electron as opposed to a flow of electrons in a current. And it can work. But these things have to be made more robust so you can stick a whole bunch of them onto an integrated circuit. So what I claim is that that's one route to do it, basically to use quantum to kind of engineer things that we know from classical world, just smaller. But there's another way of looking at it, which is to say, okay, we know from classical engineering that any technology involves some feedback to control some complicated system. So in this room we have a temperature controller. Okay, it controls the dynamics of this room, and in my iPhone we have 1 million feedback loops, and all these things control complicated technology to make something that would ordinarily just fall out of the sky fly. Okay, what if we did quantum engineering, where we did some sort of feedback so that we can take something that ordinarily behaves in a weird way, like an atom, and force it to behave in a way that we understand. So to make a feedback to control the quantum system, to force it to behave in a classical way, so we can build a lot of transistors at the atomic scale. Or you could also kind of say, well, I don't really like that. Let's actually force this to behave purely quantum mechanical and exploit the fact that it's a quantum object and use the different rules of quantum mechanics to do computation. So this is the field, the 15-year-old field of quantum computing and quantum information science that people like Paul Kwiat and Tony Leggett and experimentally I and others try to make quantum computers by, instead of suppressing the quantumness so it's small but still classical, we actually say, okay, it's small and it's quantum, and let's make it really, really robust and stable. So these are the different kinds of things that we want to do when we get close to quantum particles. But in all these sorts of ideas, I haven't really told you how we're going to build it. You see one way of building it, which involves patterning things on a surface. But it's not just electrons that are quantum particles that we can manipulate. We also have atoms at our disposal, just pure atoms. Is there something that we can do with just pure atoms that can be useful? So that's really what I want to focus on in this talk, is on the atomic side, how to manipulate atoms and do something useful with them. Okay, so toward that end, I want to describe how in the last 15 years, 10, 15 years, colleagues of mine and some of the research that I have done have moved from what I call the Stone Age of atomic physics to, okay, only the Bronze Age. But maybe soon we'll get to the Iron Age. But in doing so, we've gone from learning how to start to trap atoms, to solve the problem of cooling them down from hundreds of meters per second, flying around. We've solved how to slow them down. And then we started with some baby steps about 5-10 years ago and learning how to move them, to make them bounce, to controllably do things with them. We have trapping. And then by adding some technology from, say, Silicon Valley, kind of like making computer circuits, and melding that with quantum physics, with the atoms, we've been able to make these devices called atom chips that hopefully will create a useful device that I'll tell you about that we're trying to build in our laboratory called the atom chip microscope. Okay. All right, so let's start with how you trap atoms. So what are the first kinds of things that you would like to do? You have a gas of atoms. What do you want to do with them? The first thing you want to do is be able to learn how to push them, and you want to see that you've pushed them. You want to verify that you can do this. You want to image them, take pictures of them. So how might we be able to do this? Well, we have some things at our disposal. We have the laser. Okay, so this is a green laser right here. It has, you see the in spot here, because in the air, the green photons that come out of here don't scatter much off of the air, so they only scatter off of the whiteboard up there. But there's a stream of photons coming out. Now again, here's the weirdness about quantum mechanics. I can equally, with equal validity, say that this is a stream of waves of green light or a stream of green photons. And I'll use those kind of concepts interchangeably depending on the context. But let's just for a moment put on our pretend hat and say that instead of this being a stream of photons, which we know are massless, let's just represent that as a stream of little marbles, okay? Tiny little marbles. Now, what if we shine this laser beam onto an atom? What will happen? Well, let's represent the atom as this big bowling ball, okay? So now, say the bowling ball was rolling toward the source of the stream of marbles, the photons. So you can imagine this big bowling ball kind of creeping down this path here, and then I'm sitting here with my photon shining at it, trying to make it stop. Well, you'd say that, oh, that's kind of crazy. I mean, these marbles are so much lighter than the bowling ball. I'd have to throw, a million, a billion of them to get that bowling ball to slow down. Well, you're right. You would have to throw a million, billion of them to get them to slow down. But you can do that. Just by shining this laser light, the number of photons that are coming out of this per unit time is a million billion, okay? So I have that many photons streaming out. And so eventually what will happen is that bowling ball will start to slow down. Okay, it'll come to a rest because I've flicked so many of these marbles off of it, or these photons off of it. So that's how we can actually stop an atom. It's by shining an appropriately tuned wavelength light beam off the atom. Now, atoms are funny things. Again, they're quantum particles. That means that they don't like all colors of light. They're very particular. They only like very specific colors of light. So one atom, say a rubidium atom, only likes red light, whereas a dysprosium atom only likes blue light. A lithium atom only likes yellow light. Okay? That's just the way they are. So if you take your marbles and you have a particular color of marble, then they will scatter properly. So if you do that, then shining it at the atom will slow down and eventually come to a rest. So that's one technique that we've learned how to do in the last 20 years. Now, how do you verify that you've done this? Well, it's actually quite simple. The Nobel Prize this year was won for the CCD camera. So you take all that great engineering and thinking, and you just grab one of these guys. I even have one on my iPhone. and you just shine it, and you just capture some of those marbles. Okay, not marbles, that would hurt, but the photons. You capture some of the photons into the lens, and that projects it onto the CCD, which creates an image. Okay? So just by capturing some of these marbles, you can create what's called a fluorescence image of those atoms. So what I show here is a picture I took in my first year in graduate school of 1 million cesium atoms. So this blob here is actually comprised of not one, but 1 million cesium atoms. Cesium is actually, it doesn't like any color. It likes infrared. So it's a little bit too red for our eye to see. But the camera can still see that. Your camera in your pocket can see beyond what your eye can, just a little bit. So you can make a fluorescence image. All right? There's another way, which is to take the beam, and the atoms, since they scatter all these marbles out of the beam of marbles, they actually create a deficit of marbles, or a shadow. So you can actually just take a picture of the shadow. And that's another way to do it. And the way you choose one or the other depending on the particular experiment that you want to do. One's has better signal to noise, let's say, than the other. So then you can go into your computer and be fancy, and you can do a false color image of these things. And you'll see a lot of these kind of false color images where typically red shows that you have more atomic density than the blue, depending on how you want to use your computer to false color. So that's how we can push and image atoms. What else can we do? Well, we can combine that technique of pushing or actually slowing in one direction into 6 directions. So we just buy more lasers and shine them in all 6 directions. Okay, and where they intersect, you will slow the atoms in all directions. Okay, so normally a gas of atoms that are just whizzing about everywhere, if they come into contact with the intersection of those lasers, will completely slow down and actually almost come to a stop. Okay. Now I've drawn these coils around here. The coils create a magnetic field. If you run current through a wire, it creates a magnetic field. I'll explain how this works a little bit later. But basically, because almost all atoms are magnetic, they're like tiny little bar magnets. And in fact, that's what a bar magnet is. It's an amalgam of many little atoms that each one is a tiny little magnetic moment, or a tiny little magnetic dipole. You add them all together, you get a bar magnet. Well, each one also feels a magnetic force. And so by creating a magnetic bottle with these coils, you can trap the atoms. So what do I liken this to? It's kind of like, if you think of the lasers as, the intersection of lasers as honey, then the atoms are like a bee, okay? The bee gets stuck in the jar of honey, okay? And in fact, this is actually quite a good analogy because we actually, in our lab, in the labs worldwide, we call doing this exact thing an optical molasses. So the atoms get slowed down into the optical molasses until they stop. But of course, they kind of drift in molasses. Just like a bee, if you let it stay in the molasses for a very long time, it'll kind of drift around. And at some point, it'll drift to the edge. So you have to have a bottle to contain the whole system. So like we have a glass bottle here, the magnetic field acts as a magnetic bottle. You put these two things together, you get what we call a Magneto-Optical Trap. It cools the atoms down, and it traps them. Okay? The acronym for that is MOT, and you'll hear me talk about MOT. I'm not talking about applesauce. You'll hear me talking about a MOT throughout my talk. So this is something that our Secretary of Energy, Steve Chu, created for his Nobel Prize. This was first done in 1989, 1987, I think, 1987, 1989. And he won the Nobel Prize for this, along with a few other people who came up with theories about how this worked and some extensions to it in 1997. And now he's our Secretary of Energy. So this was a very important thing. This revolutionized our field of atomic physics. This is a starting point for everything I'll tell you about. So it takes atoms that whiz about at room temperature. So room temperature is around it's 70 degrees, 20 Celsius, 300 Kelvin. Okay, so I'll talk about Kelvin in my talk here because that's the scientific way. So room temperature is about 300 Kelvin. Doing this technique brings the atoms from 300 Kelvin all the way down to 10 microkelvin. Okay, 10 to the minus 5 Kelvin. How many orders of magnitude is that? It's a lot. Okay, that's a lot. 7 to 8 orders of magnitude. That's quite a refrigerator. It's the best refrigerator in the universe as far as we know. Okay? So that's an amazing technique. Where's absolute zero? Well, that's 0 Kelvin. Well, 10 to the minus 5 is pretty darn close. We can do better. I'll tell you about that in a moment. So this is an example of what it looks like in a laboratory. Not my laboratory, but this could have been my laboratory. These are the coils. This is a cell. I picked this because it's a particularly nice looking image because it's not very cluttered. There's a yellow circle I have, and around that yellow circle you see a little orange or reddish dot. Those are rubidium atoms. So they like red light. They glow red when you do this. So with your own eye, basically, you can see rubidium atoms right in the center, right where my green laser pointer is. Okay? It's about a millimeter or two across, but you can see it in this image. Okay? So that's what it looks like in laboratories. Okay, most laboratories, it's much more complicated, and I'll show you some pictures of my lab in a moment. Okay, but what else can we do? Well, so far I've been talking about the atoms in this picture as big bowling balls. They're point-like particles. They're just moving around with like billiard balls. Where's that particle-wave duality coming in? Well, it turns out if you cool things enough, make them cold enough, then that wave nature starts to become manifest. So if you take a bowling ball and make it near absolute zero, instead of being a nice, hard, spherical object, it'll start to get fuzzy around the edges, start to be a little bit wave-like. It's true. It will, as far as we understand quantum mechanics. Now, it's a little hard to do that with a bowling ball, but with an atom, I just showed you that we can get to 10 to the minus 5 Kelvin. Okay, that's 10 microkelvin. That's getting kind of close to absolute zero. Do these atoms start to get fuzzy then? And they start to deviate from being like point-like particles? Not quite at 10 microkelvin, but if you make them a little bit colder, they start to. So how can you make them colder? Well, so this is what I'm trying to describe, is that at the beginning they act like particles. Here they start, if you get them a little bit colder, they start to act like little waves. Eventually, if you get them cold enough, the wavelength of those waves get larger and larger, and they become so large that they overlap with their neighbors. So the mean free path, the wavelength becomes on the order of magnitude as the mean free path between the particles. At that point, they start to overlap. And you can't really tell the difference between the atoms. It all just looks kind of like one wave. So if you make it cold enough, you really, in principle, cannot tell the difference between each atom, the wave from each atom. They all look the same. And in fact, they condense into one macroscopic wave. So that picture I showed you of that ball of cesium atoms or rubidium atoms, if you make that cold enough, that will condense into one macroscopic wave that you can see with your eye. Okay? So this is a big quantum blob, quantum superfluid. And in principle, you can see with your eye. Okay? So this thing is called Bose-Einstein Condensation, because Bose, an Indian physicist, and Einstein, way back when, proposed that this could happen. Okay? This was a long time ago, I think in the 30s, when they proposed this happened. And it's been seen in helium and other things, but the first time it was seen in purely atomic systems, in a gas, was in 1995. And the folks who created this won the Nobel Prize for it in 2001. So atomic physics has done quite well in the last 10 years in developing this technique. And what's so fascinating about this is that this is a truly quantum system that is macroscopic, that we can observe without any disorder. If you take interesting condensed matter systems like a superconductor, it's a very nice system. It's quantum mechanical, but there's a lot of disorder. There's dirt in this thing. This is a pure quantum object. So here's an image of one of the first Bose-Einstein condensates, or BECs as we like to call them. At high temperatures, all the atoms are kind of like these balls or like this, and they get this dense kind of, diffuse Gaussian blob. But when you go to colder temperatures, so this is maybe 1 microkelvin, when you go a little bit below 1 microkelvin, some of them start to collapse into one wave, and then when they're really, really cold, they all collapse into one macroscopic quantum state. So there's one little spike in the image, in the density. They all like to come together to one little blob. So you get this spike in the density when you take the image. Okay, you see this really bright dot. This happens around 100 nanokelvin. Okay, well, we're getting really close to absolute zero. And in fact, some experiments have gone to 100 picokelvin, 1,000 times below this. It's certainly the coldest things in the world by far. And as far as we know, there's nothing else in the universe that can be colder. to, maybe there's some laboratory on another planet where they're much more advanced and they can go colder. But no natural phenomena that we know in the cosmos can do this. So that's really exciting. What can you do with these things? Well, there's a lot of things that we can do. And I'll describe one application later in my talk. But this is an example of that particles really do become like waves. Okay, they collapse into one little wave-like property, this little delta function from an incoherent billiard balls. Okay, so one application of this, of being able to manipulate and cool atoms, we already know. And in fact, a lot of us have this kind of in their own pocket, more or less. And this is GPS. So GPS is based fundamentally on atomic physics. How so? Well, the best clocks in the world are from the ticking of atoms. So each atom you can look at in a cartoon way as a nucleus, an electron that orbits around it, or maybe many electrons. Okay, that's not quite right. The electrons are actually this fuzzy wave around it. Okay, but let's just look at it in this picture. And when a photon comes, it can promote the orbit of an electron to a larger orbit. Since it orbits further out, that's a different energy. There's an energy difference. If the energy is the same energy as the photon energy or the photon color and energy are actually similar, then the electron will go up and then it will come back down. And then if you do it again, it will go up and come back down. It's kind of a little tick back and forth, up and down, up and down, up and down, up and down. And that frequency, that energy difference, which is kind of like a frequency of it going up and down, is the same for that type of atom, no matter if I have the atom here, if I have it in Boston, or I have it in Japan. At least that's as far as we understand. Okay? All atoms of a certain type, like cesium, let's say, they're all the same. So each one will tick at exactly the same rate. So if I build a clock with cesium here, it's going to tick at exactly the same rate as my friend's clock in Japan. That's a great clock. It's particularly a great clock if we want to measure something simultaneously, say a signal from a satellite. So if I want to measure a signal from a satellite at different places on the Earth, I better have the same kind of clock that ticks in the same way. Okay? Moreover, if I want to measure the signal from many different satellites, I want to not just have the same type of clock, but I also want to have it so precise that I can measure the difference in time it takes for signals to go from one satellite to another satellite. That difference can tell me, through what's known as triangulation, my position by just measuring the time it takes to get from here to there, here to there, and here to there. It takes a little bit of time. I can pinpoint myself. But darn, you got to have a really good clock, okay? Because these signals move at the speed of light, and that's really fast. That's 3 times 10 to the 8 meters per second. So you have to have a clock that's very accurate and it's the same everywhere. Well, that's what atoms do. Okay? So this is an example of the primary standard for timekeeping in the United States. It's at NIST, the National Institute of Standards and Technology. This one is at Boulder. And it fits on a laser table, kind of like my laser tables. And basically, it looks at cesium, at how a cesium atom ticks as you shine photons at it. It recounts how many times it ticks in a given period, and that sets the clock. That actually is the definition of the second. Okay, so it's so precise that we defined our whole concept of time with it. All right. So by doing this, we could time how signals go back and forth between satellites, and by recording that on a handheld device, you can pinpoint your position. So this is an example of where modern atomic physics, the ability to trap atoms, make them cold, and observe how they tick, has enabled us to have this technology that really is quite prominent in our life. Okay, so what's the next step? So we've learned how to trap them in one spot and make them very, very cold. You kind of now want to move them around. Let's move around. Like, it wouldn't be enough in a circuit to just have electrons being confined to one spot in the computer. We got to have the electrons move around and do things. Okay, here we got to have the atoms move around and do things. So what's the first thing that you would think about doing if you have a trap? Well, the first thing that I would think about doing is dropping it. Gravity's there. We're on Earth, not in outer space. So let's drop it and see what happens. Okay, let's do that. Well, in the late 90s, folks did this with a Bose-Einstein condensate, and they get these beams, either pulse beams or straight beams of atoms coming down. Okay? Gee, that kind of looks like a laser beam, doesn't it? It looks like a laser beam. In fact, it is. This is an atom laser. So one thing I didn't tell you about the Bose-Einstein condensate is that it actually is the same thing as a laser. Okay? So a laser is a coherent supply of photons. So the photons that come out of my laser pointer here are different than the photons that come out of this light bulb. The photons that come out of the light bulb, they could be the same green color. I could put a filter on. I could focus them and collimate them sort of in a beam. I can make them look exactly the same as the green photons coming out of here. It's just a light bulb. But there's a fundamental difference. The light that comes out of the light bulb, no matter how intense or narrow it is, the photon waves oscillate up and down incoherently, out of phase with one another. They're random, just a random mishmash of waves. Okay? So the wave of one photon has a completely uncorrelated phase with the wave of another photon coming from the light bulb. In every other sense, it's different from this, where all the waves are in sync. They all march in step. They're very disciplined photons. Okay? And these are chaotic photons, random photons. Okay? In the same way, a gas of atoms is like a thermal light source. The atoms can be they're the same atoms. They can have the same number. They can have the same flux. I can shoot them all in some direction with the same number coming out. But if they're not Bose condensed, the waves associated with those atoms are all out of phase. Okay? But here, in these atoms here, the wave associated with each atom is exactly the same phase as its next atom. So those atoms are all kind of locking in step. They're marching to the same tune. Okay? So if we bounce the atoms kind of like doing this, then we've created an atom laser. If we drop them, we have an atom laser. That's what a laser is, basically. It's a coherent source. And here it's light, here it's atoms. Okay, just like with a laser pointer, and if you're doing anything with lasers, say at the grocery store, and you want to read the barcode, you need a mirror. Okay? So how do you reflect them? We can drop them, create a beam of them. How do we reflect them? Well, again, we have a handle onto the atoms. Our tweezer is a magnetic field. So that tweezer I talked about earlier, that's a magnetic field. I can grab onto an atom. I can move it around with a magnetic field. Okay, so this is an experiment I did when I was a graduate student where I decided to reflect a cold cloud of atoms that were falling. So if I want a magnetic field that can reflect atoms, it has to be large because so each atom has a very small magnetization. Where's a large source of magnetic material? Well, we have it all on our computer hard drives. Okay? The material inside a computer hard drive is some of the most magnetic stuff we have on Earth. Okay? So if you open up a computer hard drive and take out the disk, then you have a really good magnetic platter. Okay? So that's what we did. Just grabbed an old computer and ripped it apart. And then we took it and we patterned this little kind of diffraction gradient on the surface. So what we did was we etched out little stripes, these black stripes, like so. So we removed some of the magnetic material in stripes and left the magnetic material in these light spots, okay? Light stripes. So that's a real image of it. If you actually take an image just of the magnetic domains, which you can do, then it looks something like this. So you have these kind of gray, just homogeneous gray stripes that are the same stripes as these black stripes. But in the middle, you have these dark and white stripes. Those are the zeros and ones of the hard drive. So this was somebody's PhD thesis that I just destroyed. So basically, you have these stripes of 0 and 1, 0, 1, the north, south, north, south, north, south, north, south, in some random pattern, or maybe someone's thesis. If you just demagnetize that and remagnetize that in one direction, all those north and south line up against the boundaries of these etched lines here, and you get a black and white, black and white, black and white stripes. Okay? It turns out, and once many of you take your 200 level physics course, you'll be able to calculate this yourself, that if you align a bunch of north-south magnetic bar magnets and calculate the magnetic field as a function of position away from this, the magnetic field decays exponentially. Or in other words, as you get close to this, the magnetic field increases exponentially. Okay? So if you have an atom that feels a magnetic force, is repelled by a magnetic force, as it gets close to the surface, it sees an exponentially increasing magnetic field or magnetic wall. It's going to say, I don't like this. I'm going to go the other way. Okay? So an atom that falls onto the surface will get reflected by that very steep, high gradient magnetic field and be repelled. Does that work? Well, here's the experiment I did. I trapped some atoms here. You can't see them. I just wrote a little dot. And here's the sample of that hard drive. This is in a vacuum chamber, so there's no other atoms, more or less. This vacuum is nearly as good as outer space. Have very good pumps to suck everything out. Sprinkle a few cesium atoms in, shine in the lasers, which you can't see because they're infrared. You can trap the atoms above that patterned area, and then you just turn off the lasers, and the atoms fall down. Now, as the atoms fall down, you can take images of them as they fall, and you can see that they bounce just like in your high school physics class when you calculate how a ball bounces off of sort of bounces up and down like a parabola. So it works. So here's a little movie of that. I hope you can see. So the cloud, you see it start up, it falls, bounces up. You see maybe 2 or 3 bounces. It also expands because it's hot. So as it falls, the atoms expand out. They bounce and they continue to expand. So this was done about 8 years ago or so, or maybe 6 years ago, 7 years ago. So since then, people have done this with Bose-Einstein condensates. This is just with a thermal cloud. That's like bouncing, making a mirror for thermal light. Later on, people did it with a laser, an atom laser, and it works pretty well. Okay, so now we can bounce things. So that's pretty nifty. That's not sufficient for making new technology. You need to do some more things. Okay, so before I tell you about how we go to the next step of really being able to trap things and move them around, let me describe another technique we have, magnetic field imaging. So I hope you've seen that magnetic fields are a nice tool for moving atoms around. How can we engineer those magnetic fields so we can move them around more precisely? Well, let's revisit some of the things that we know about magnetization. If you take a wire and you run electrons through that wire, a current through the wire, a magnetic field is created. Okay? The moving electrons create a magnetic field. And in particular, that magnetic field kind of curls around the wire, like so. So it's a circular magnetic field around the wire. All right? So the current goes like this. You get a circular magnetic field around the wire. Everywhere where the wire goes, there's a circular. The magnetic field gets smaller as you get further away from the wire, but it's always kind of the circular thing. Now, what if you take that wire and then wind it around itself? Well, that's what a solenoid is. So you have a solenoid in your car, you have a solenoid all over the place. It's just a spool of wire. So if you take this curly magnetic field, and then look what happens when you change instead of taking a straight wire, you make it a coil. It turns out that these magnetic fields kind of combine to form a very large and homogeneous magnetic field in the middle of the solenoid. Well, that's a very nice thing. Now we can create magnetic fields that are very smooth wherever we want them. Unfortunately with this, they're inside of a spool of wire. How am I going to get laser beams inside there to trap the atoms in there? That's not so great. Well, okay, I can split the wire into two, the spool, separate the two sides, cut it in half and separate them, and that's these coils of wire. So that's what I was telling you about earlier. If you take two coils of wire, split them across, you have what's called a Helmholtz coil. After Helmholtz, who calculated this first, I assume. So now you can create this is like a split solenoid. So you can create a homogeneous magnetic field in the center that you can stick laser beams in and out of. So that's a really nice tool. Okay. So what else? So let's use that as a way to trap atoms. But on the other hand, I'm talking about coils of wire that are this big, and that's not really great for making iPhones. All right, I don't want to have a big kind of coils of wire around this guy. That's not so much fun. Is there a way to miniaturize this? And do we gain anything from miniaturizing all of this? Well, yes, actually. Something that we discovered about 10, 12 years ago is that you can make these big coils of wire for trapping atoms in a miniature fashion while being able to actually trap the atoms more precisely and in a stronger way. It turns out if you shrink a coil, the tightness of the trap, the magnetic field that you can trap the atoms with, say the gradient of that, the force, scales as the 1 over the size of the coil, or the size of the wire, or the spacing of the atoms from the wire. So 1 over r squared. So if you make r really small, since it's on the denominator, the entire quantity gets really large. So let me show you how that can work. So let's take, again, our favorite wire like this, run current through it. If we look at it end on, we see this curling magnetic field like I showed earlier. Now let's take our Helmholtz coil, our split solenoid, and put that perpendicular to the wire. So if we put it perpendicular to the wire, then you'll see that we combine these two things and we get this gradient magnetic field that looks like this. Okay? Those two fields cancel at one point directly above the wire. Okay? One point directly above the wire. And so this field will cancel this guy, and you'll get no field in the center, and everywhere else you'll get some larger field. Now if I have an atom that hates magnetic field, that is repelled from all magnetic fields, it's going to settle into the middle here, where these two fields cancel, right in the center. Okay? So here's the wire I'm looking at end on. Here's the surface that I place it on. I want to place it somewhere because this wire, to get these large gradients, has to be very small, even micron size, 10 micron or micron size. So I have to glue it onto some surface in order to make this work. And if I do that, then I can trap the atoms above the surface like so. So that's a miniaturized atom trap, or a magnetic microtrap. And just by changing the current to this wire, or this bias field, I can change the position of that zero magnetic field and move the atoms up and down at will. Okay? I can move the atoms. That's great. One other feature is that, well, I have the wire goes all the way out of the board. So this is like a tube. This is an atom guide. So the atoms can move them up and down, but they can also expand in one direction. So now I have a guide for the atoms. Wherever I route that wire, the atoms will follow. Now say I don't want to follow them, have them follow the wire. I want them to stay in one spot. Well, then I can just design the wire so it pinches in two spots, like so. It'll pinch this U-trap here. If I do that, then I just create a little cloud right above the center. Okay? So that's called a U-trap, because the wire looks like a U. Okay? So here's a picture of a real U-trap that I made a long time ago. These are cesium atoms. This is a gold surface with little gaps of gold that define this U-shaped wire. All these little star-like flecks are just dirt on the surface. And the atoms are this white blob up here, white cloud of cesium atoms. If I look end on, sure enough, I see this cigar-shaped cloud. And since the whole surface is gold, it's kind of like a mirror, I can see a little ghost image down there. Okay? So here's a movie of bringing the atoms into the surface. So I'm changing the currents in the wires, starting them out really high up, and then I bring them closer to the surface. You see as I get them close, you can see a mirror image. They don't stay forever because background gas knocks the atoms out of the trap. But in other subsequent experiments, this lasted for maybe 100 milliseconds. In other experiments, you can hold this on for a minute. Okay, hold them there for a minute. Okay, so this is a magnetic microtrap. This is a fundamental element that we will combine as a tool to build a laboratory on a chip. So these are atom chips. So you can go into clean rooms, or I can go into, my students will go into clean rooms, and you can go, just like you're in Silicon Valley making a computer chip for your iPhone, you can go and pattern gold wires that are micron scale onto silicate surfaces and create all sorts of neat patterns of wires in all sorts of ways, and each one has a different functionality. And each one, when you run current through them and put atoms in them, they can route the atoms any way you want. You can switch the currents on and off, you can move them on the surface deterministically. So you have a laboratory on the chip. That's great. We can actually start doing things with the atoms. Here's an example of each one of these wires is 1 micron. You run the currents in the right way, I could take a cloud of atoms, split it into two, and recombine it. So this is something that we built about 5 years ago or 6 years ago. Okay, so here's just a quick example of one thing that you can do to move them around. So this is loading a wire guide. So we start with, now we hang everything upside down, so the atoms are actually upside down from the surface so that we can shut everything off and the atoms will fall into gravity and expand. And from that expansion, we can measure the temperature. How quickly it expands tells us the velocity, and the velocity tells us the temperature. So everything's upside down. So we initially trap those cesium atoms like this, and they're positioned along these wires. There's this D-shaped wire here. This is kind of like a U wire, but it's curved. Here's other wires. They're straight. We trap them far below the surface, like right here. Then we change the currents and bring them closer to the surface. Bring them very close so you can start to see the mirror image. And then change the current pattern from going from this wire, like so, to the D-shaped wire. Okay? Now what you can do with the D-shaped wire is you can change the angle of the bias field. So instead of coming along this direction, it goes along this direction. You just rotate it. And as it rotates, the atoms will slide around this curved portion over to here. And here's another image of it slid around. Okay? And now you can just change the current from this D-shaped wire into these other wires down here, which are hard to see. And the atoms transfer over to this wire, And then by opening the gate, by turning off the current that goes through this wire, we can shoot them all the way down here. So this is an image of them down in this area here, and they actually expand all the way down from here in real space, a centimeter. They travel a centimeter all the way over to this region. So we can controllably shuttle them around on the surface. So what are we going to do with this? So I promised you some technology. So this is something that I'm starting in my group upstairs, and actually some of my students are here who are actually building the apparatus as we speak, or they will after the talk is over, is to make an atom chip microscope. Okay, so here's a sketch of what I just showed you. So we can trap the atoms above this region, and then we can shuttle them over to another region. What if we sandwich between the atoms and the surface some interesting material? Some condensed matter material, some solid state material, some interesting material that the atoms, because they're so close to it, will be perturbed by that material. The atoms will actually sense, say, the magnetic fields or electric fields emanating from that material. Well, then you can use the atoms as a microscope to probe those magnetic fields or the properties of that material. Okay? So let me explain that a little bit more. Basically, we've already done this. So when I was a graduate student, we did the same sorts of things, except this material was actually a trap for photons. There were two parallel mirrors that confined photons. And we brought the atoms to where the photons were to try to forcibly make atoms interact with confined photons. I won't describe that very much now, but that was a way in which you can think about creating a quantum computer. But here in my lab, we want to actually image materials. So what kind of materials would you want to image? Well, one very interesting material would be a superconductor. So there's these materials that were discovered in the 80s that conduct electricity without resistance up to temperatures that are cold by our everyday standards, but far greater than all the other material, all the other superconductors that we knew in the past, which were close to absolute zero. So around liquid nitrogen temperatures, liquid nitrogen, that's that gassy stuff that you could play with and freeze bananas and crack bananas. Even at that temperature, the materials would allow electrons to flow without resistance. That's pretty deep. So this is one of those materials here. One weird property of them is that they expel magnetic fields, so you can get them to levitate above a magnet. But that's great, and there are companies that try to make cables out of this material, but they all have to be chilled to liquid nitrogen temperatures. That's not so great for my iPhone. I don't want something so cold in my pocket. So how do you actually make a material that is room temperature superconducting? Nobody knows. If you know, you'll get a Nobel Prize. So half our physics department here is trying to figure this out. Almost half. Okay? It's been a problem. It's one of the greatest challenges of modern physics. So what if you can create a tool that will allow you to image those materials in a way that no one else has ever done, to actually see those materials in a way that no one else has ever seen? Well, that's what we're trying to do. Okay? So if we can improve the temperature from, say, 77, the highest ones are about 135 Kelvin, to room temperature, we can think about doing things like revolutionizing our nation's power grid, for instance. Okay, big time improvements. So how can we do this? So this is the image of the atom chip microscope. So what I was telling you is that you can trap an atom, now let's talk about, instead of just thermal atoms, let's talk about a Bose-Einstein condensate. So this is a wave of atoms. Let's look at a cigar-shaped wave of atoms. Above this wire, here instead of a U shape, it's a Z shaped. It's a little subtle difference of how the magnetic fields are. It's a little bit better to do it in a Z. So you can trap the atoms in a tube above the surface. You actually saw images of that, but here it's a wave of that. It's an atom laser that's confined. You can take images of it by shining a laser and casting the shadow onto a CCD camera here. Now what we've seen is that even if you go to extreme lengths to make a perfect gold wire on a surface, the crystalline structure of that wire is not homogeneous. There's a little defect. Great. So the way the electrons flow through that wire is not in a parallel fashion. They actually move around a little bit. And that moving around at the part per million level, that little squiggling around, is enough to change that wave, matter wave of atoms. Actually split it off into these little cigar shapes. Okay? It's true. The magnetic fields at the part per million level are sensitive enough, the atoms are sensitive enough to split off like this. Why? Because the atoms are so light. And they're sensitive to magnetic fields, but they're so light they can be moved around by these perturbing magnetic fields. Of course, you could take an image of that, and you can see these little indentations in the density. And you record that. And that is an artifact of the underlying inhomogeneous magnetic field. So then if you do something where instead of having a gold wire, which is kind of boring, you actually replace that, or over to the side, you shift the atoms over some interesting material and do the same thing, then the way in which the atoms get perturbed is a signature of the underlying magnetic fields that emanate from that material. Now, I showed how you can move atoms around over a surface. If I just move them to a different position, take a picture again, I see a different pattern. Move them again, I can raster across the whole thing and create a field of magnetic field profiles. Okay? And a colleague of mine did this just a few years ago. So this is an image of the magnetic field over a wire. Okay, it wasn't an interesting material, but nonetheless it proved that this could work. And the sensitivity here, the smallest little feature, is at the few nanotesla level. Okay? Here's a big 300 nanotesla spike. Just to compare, Earth's magnetic field is 50 microtesla. We're talking about nanotesla. Okay? That's a sensitive probe. All right? So here's the experiment that we're building as we speak. Some of the people who are building it in the audience. We have an oven where we heat the rubidium atoms. They send it down this tube. It's kind of like a decelerator. It's like a particle accelerator in reverse. Okay? And then they get trapped in this region over here. We use the stage with some optics to then grab onto the atoms with light, like an optical tweezer. I haven't explained how that works, but you can grab atoms with magnetic fields and optical fields. That tweezes them out into another chamber over here. That chamber will be a big cryostat where we can simultaneously have an atom chip trapping and something very cold. So we use liquid helium to make things very cold. So we can combine two technologies, making cold samples and this great imaging. So what's a kind of scientific application that we can think of besides superconductors? Well, there's a whole host of materials that are called strongly correlated materials. What that means is that the electrons inside these materials don't behave like they're individual, one electron here, one electron here. Those electrons are correlated. If one moves, all the other ones have to move out of the way in a correlated fashion. And because they do this kind of big, giant dance step, the electromagnetic properties, how it creates magnetic fields, electricity, all these things, can be very interesting and useful technologically. Okay? And so one weird thing about these materials that prevent us from really understanding them at a deep level is the fact that you could have simultaneously a metal and an insulator at the same time, and the insulator can develop into a little patchwork of little droplets as you say tune the temperature of it. If you start developing this kind of Dalmatian-looking pattern of insulating droplets, well, the current flows in a weird way around that. People just don't understand how that happens. It's very difficult to actually calculate how these puddles develop and move around and combine. So if you had a way to image how the current flows around those puddles, you may be able to develop a theory that can describe it, and then use that theory as a predictive way to design new materials that will actually exhibit these properties in a technologically relevant way. So this is one thing that we can image. Okay, that no one else has ever been able to image. So I claim that this is a great imaging technology, but I also have to tell you how it compares to existent imaging technologies. So one standard technology is called a squid. You don't take something from the ocean that's slimy and put it near a surface. A squid means a superconducting quantum interference device. Okay, it's a big loop of superconductor, like so. It can be down to about 10 microns, but generally it's a little bit larger. You make it very cold, it superconducts, but that superconductivity is very sensitive to magnetic fields. Remember, you saw that magnet that was being levitated by that superconductor that was being levitated by the magnet. Well, that same kind of interaction, or the fact that superconductors are very sensitive to magnetic fields, can turn this device into a probe. Another way that people try to measure magnetic fields is that they take a little diving board with a little magnetic tip near some material, and the way in which that diving board oscillates changes depending on the magnetic field that magnetic tip senses. Okay? That's called a magnetic force microscope. So here's my plot of how well my technique can do with respect to them. So on the x-axis is resolution. So this is the benchmark for how small of a feature I can measure. Okay? So this is 1 micron right here. 10 microns, 100 microns, millimeter. You can see this with your own eye around here. Okay? This is sensitivity on the y-axis that's measured in Tesla. So Earth's magnetic field, just for some benchmark, is way up here. So MFMs actually measure around Earth's magnetic field, but they do so with very high resolution. They can really get down to tens of nanometers or even better. On the other hand, you have these squid devices, which have incredible sensitivity, but they're kind of big, 10 microns, 100 microns. So we've already demonstrated rubidium atom chips. Colleagues of mine have demonstrated atom chips that are right in this kind of middle range where we have no technology, no way to see it. It's completely dark to us. So we can see phenomena at this region here. Now what I claim is that the best you can do with the atom rubidium is given by this line here and this line here. Basically, if you go with this line here, you can't trap them with respect to gravity anymore. Your trap is so weak they fall. And if you go too far this way, you can't see them anymore because you're limited by the wavelength of light to be able to see something. Okay? Now if you use dysprosium, say you want to use the best atom possible for this. Let's use the most magnetic atom in the periodic table. Then because it's so much more magnetic, we can trap it better, and you can get all the way down to this level here. Basically, you sat right here, you would be able to see things that no one else has seen before. Sounds great, huh? So there's a few other things that we can do. I won't go into these in detail. But the other thing is that even though the atoms are the coldest things that we have on Earth, they don't care how cold they are a micron or so above some surface. There's no temperature conduction. They're in a vacuum chamber. Radiation doesn't couple to the atoms because the atoms are very particular about the color of light that they like to see. So the thermal radiation does not affect the atoms at all. So that surface can be room temperature while the atoms are 100 nanokelvin. Wow, that's a huge temperature gradient. But the atoms don't care. So unlike squids, which themselves have to be cold in order to work, and so do these things, because they're so big, whatever they're measuring also has to be similarly cold. And this device, the thing that you're probing, can be whatever temperature you like, and the atoms don't care. So we can measure temperatures, we can measure this phenomena all the way up to high temperatures, and no one cares about it. Okay, so we can see things at high temperatures that no one else has seen before. There's other things that are very interesting, which I'll skip. So I said that dysprosium would be the ultimate. So I'm not just saying that as some futuristic thing. We are actually trying to trap dysprosium. And we did the first trapping of it about 6 or 7 months ago in my lab. So one of the people who was involved with that is sitting up there. So we created the first dysprosium Magneto-Optical Trap. This is a very strange thing. Dysprosium is a very complicated atom. It's at the bottom of the periodic table. It has hundreds of electrons. It's not a simple atom that your grandfather, who's an atomic physicist, would have known and loved. Okay? This is a weird thing. No one's ever done this before. So despite how complicated the atom is, we're able to make a sample that's a millikelvin in temperature. And we now have 500 million of these atoms to play with. They're the most magnetic things around. So this is a picture of the apparatus that's sitting up 2 floors above here in Loomis. And here's a little glowing ball of the atoms. It turns out dysprosium likes blue light, so they glow in a blue color. This is part of the vacuum chamber. So what can we do with this? So besides making the world's best atom chip microscope, just the fact that these atoms are so magnetic allows us to see new phenomena. If we make it really cold, so cold that we make an atom laser, or a BC, out of this magnetic thing, then what we've in fact done is made a quantum ferrofluid. So ferrofluids in the classical world are like colloidal suspensions in oil of little iron particles. Here, and those are known, if you put them near a magnet, they form these weird patterns. We don't know what kind of patterns will form with a quantum ferrofluid. No one's ever seen this stuff before. So that's what we're going to do with this weird dysprosium atom, which is highly magnetic. Okay, so technology often has humble roots. So the first computer was in a huge room and couldn't even send an email or anything. Okay, it was UNIVAC. And the first transistor looked like something I would build. It was horribly ugly, the size of a golf ball. Okay, I can't be too dismissive of it. It was created by our John Bardeen, who everyone knows and loves, and worked upstairs. But these things lead to real technology. Nowadays, we can put millions of these things on a platter that's the size of about 4 inches. Okay, that's led to the iPhone. All right, so it has very humble roots, but it can do amazing things. In particular, lasers, when they were first invented in the 60s, people thought they were a joke. They said, oh, these are a novelty thing. You should sell them in novelty stores. They'll have no practical application. This is completely worthless science, worthless endeavor. Who funded you? Okay? Well, we know that's wrong. They're everywhere. My father, who's an ophthalmologist, used these every day. They're in CDs. I have a laser in my hand. We often have lasers in our pockets. They're everywhere. Okay? So what's in store for the atom chip? I don't know. But it's important to remember sometimes that a chip is just a chip. Okay. So with that bit of humor, it wasn't as good as your joke, but I'll conclude and say that atomic physics at Illinois is growing. We have 3 members of our group. The other 2 members are very established and produce amazing work with BCs and with photons and quantum physics. My lab started renovating about a year and a half ago. It was just an empty storage room. Within 6 months, it was renovated. And within a year, we created the first, actually within 6 months, or 7 months, we created the first Dysprosium MOT. We're now another 6 months later, and we're building the atom chip microscope right now. And I'd like to thank my very hardworking graduate students and postdoc. Brian Cash is in the audience. Seho Yoon is in the audience. So there's Brian, there's Seho. You can talk to him after this. And I have very generous funding from multiple grant agencies. So thank you very much.
Thanks very much, Benjamin. Maybe we can take just a couple of questions. Yes, please.
You have a series of experiments that are very intriguing. How do you decide what your next experiment is going to be?
Well, that's an interesting question. So we all try to come up with a long plan of things that we want to do. So there are some recognized holy grails of physics that you want to try to address with your experiments. So you try to design your experiment towards reaching those holy grails, being able to understand high-temperature superconductors or create novel quantum ferrofluids. So you design your experiment toward doing that, but inevitably, unfortunately, as you go along, you end up discovering a lot of other interesting physics. So for instance, with our dysprosium, the Magneto-Optical Trap works in a way that we've never seen any other one in the past work. So we kind of took some time to understand that, and that ended up being a very interesting piece of physics. And so we kind of go along steps and learning kind of in a, not a random walk, but a direct walk towards these big scientific goals. But in the meanwhile, we kind of pick up interesting physics along the way. That's what makes it exciting.
At quantum levels, don't you have to deal an awful lot with the uncertainty principle? And how do you get over that?
Okay, so the uncertainty principle is a bit of an overblown concept in the sense that it's, some people think that it's the most salient piece of quantum mechanics. So what is the uncertainty principle? The uncertainty principle states that there are special pairs of quantities for which it is impossible to perfectly measure both of them simultaneously. Okay? So for instance, position and momentum, energy and time. These are 2 examples of pairs of quantities. So if you're in the quantum realm and you want to have perfect understanding of both of them, it's true that you can have problems. But it turns out it doesn't really matter for these kinds of experiments because we're not simultaneously trying to measure at the same exact time a position of something and its velocity. Okay? So as long as you're not trying to do that, the uncertainty principle has no bearing. Okay? It does mean that you can never cool something to absolute zero. That's true. But you don't need to do that in order to do interesting physics. Now, there are people who spend their careers probing exactly that, and you can do very interesting things. We can also come up with very interesting tricks by using that feedback loop that I showed to get around the uncertainty principle, to simultaneously measure 2 quantities very, very well. Not perfectly, but very, very well.
Is there a PEC equivalent to a SQUID?
To a superconducting quantum interference device? Well, it's a very interesting question that you asked, because essentially what's going on inside the squid is a VC. So a superconductor of electrons, those electrons pair together. This was the subject of Bardeen's second Nobel Prize. He's the only man who's won, or person who's won 2 Nobel Prizes. Those electrons form pairs. And when they form pairs, they condense into a Bose-Einstein condensate, more or less, a superfluid. So really, a squid is a BEC, a superfluid of pairs of electrons called Cooper pairs. Okay. With atoms. So this is something I tried to do as a graduate student, where I had a ring of atoms, and I tried to make a little junction, okay, a little bump. We weren't quite successful. People a few years after that did this with splitting atoms and seeing Josephson oscillations. So more or less, yes, you can do that. It's not clear whether it's good for anything. So.
I always wondered why iron is more magnetic than other metals. And do you have a simple explanation about what is a mu metal, what is a really magnetic metal?
Okay. So mu metal is not necessarily a magnetic metal, but we'll come back to that. So iron is very magnetic. There's other things, cobalt, dysprosium, the rare earths that are very magnetic. So what makes something magnetic versus something not magnetic? So magnetism comes from, one way to look at magnetism is coming from the motion of electrons. So if you look at an atom in which you have electrons whizzing around, it's going to be more magnetic. So as an electron kind of moves around in a circle, it produces a magnetic field. It's like a mini solenoid. Okay? So it moves around in a circle, produces a magnetic field. Has spin, or has orbital angular momentum. So that forms a little bit of magnetic field. If you have a lot of electrons doing this simultaneously, they all build up together. So atoms like iron and dysprosium and other lines like that, they simply have a lot of electrons that are moving together in concert to create these magnetic fields. Now, a mu metal is something that is very it doesn't necessarily exhibits a magnetic field itself. Actually, you use it because it does not. What it does is it allows magnetic fields to penetrate it and not, or allows magnetic fields to be conducted through it and not penetrate it. So you use mu metal as a shielding. Okay, it's high permeability.
I think if folks have more questions, you're welcome to come down front, talk with Benjamin. His students and postdocs will come down too to answer your questions. We really appreciate you coming today. We hope to see you back in 3 weeks. Have a nice Thanksgiving in the meantime. And let's thank Professor Benjamin.